All right, hey guys. Hi everyone. I think I'm live. Right, if you guys can hear me, can you give a thumbs up in the chat so I know I'm going live? So I know that you guys can actually see me. Okay, awesome. Awesome. So I wanted to know how many of you guys are currently taking AP Chem? Anybody taking AP Chem right now? I think most of you, right? Okay, so all right, awesome, Natalie. So a little bit about me. Yeah, I'm a veteran too. A little bit about me. I took AP Chemistry last year. It was my favorite class. I absolutely loved chem. So I'm really happy to be back and streaming and helping other people learn AP Chemistry. I think it's such a cool subject. So how are you feeling about AP Chem right now for those people who are taking it currently? How are you feeling about the course? I know when I first started AP Chemistry, I mean in the first 2 months, I remember thinking wow, I'm actually taking AP Chem. This is crazy. I used to look at AP Chem and think that's the course that those geniuses can take. But honestly, you don't have to be a genius to learn it. I think people are they're exaggerating on how hard it is. I think it definitely takes a lot of work to learn the concepts. But I mean, with Fileable, you can learn stuff, and there's a lot of resources on YouTube too that I can share with you guys if you ever want some tips on certain subjects, because there are certain subjects that I struggled with, and I viewed some YouTube videos, and it really helped me. So I think we can get started soon. Yeah, so I'm Serene. I'm currently a high school senior, so I'm in the college application stage, and yeah, it's a lot of work, but yeah. So I'm gonna start with my slides right now. So today we're gonna cover. Hold on, I'm gonna present this. Wait, hold on. I'm gonna do another view. Presenter view. All right. So today we're gonna go over the composition of mixtures, and so what chapter are you guys on? So what are you guys currently covering in AP Chem? I know different schools have different paces, have different pacing, so it's all a bit different. So what chapter are you guys on? What are you guys currently learning? Could you let me know in the chat box? That would be really helpful. Reviewing electron configurations. Okay, nice. So have you guys already covered mixtures and compounds and molecules, things like that? Yeah, I don't really remember what I was doing at this point in time last year. Okay, sort of. So yeah, mixtures, they're not I feel when I first covered it, it wasn't this huge topic, right? It was just they just made some basic comparisons, and they went over the basic definitions of mixtures and compounds. But I know later on there will be things that involves mixtures. There will be more complex examples and complex chemical reactions that involve you knowing the difference between a mixture and a compound, and a pure substance, especially. So yeah, so today we're going to go over mixtures, and we're also going to go over some advanced topics that involve mixtures. It's not going to be too advanced, but I'm going to kind of give an overview and tell you guys why we need to know what mixtures are, because I know at the very beginning of AP Chem it's why am I learning about mixtures? What does it have to do with anything? But yeah, so we're going to cover a lot of ground today. We're going to go, okay, so I'm going to let you guys see the agenda, so the schedule. Okay, so first of all, if you guys aren't following Think Fileable social media, you should, because there are a lot of great memes on there. I read it quite often to see what memes there are, and also you guys can also follow the schedule. So I know on Instagram story, on Instagram, I know Fileable often posts stories on what streams are set for today, or what streams are coming up. So you want to be in a know for that, because these streams are really helpful for AP subjects. All right, so today we're going to go over mixtures. So what are mixtures. We're also going to go over how to separate mixtures, and this is so important. Like, this is on every single AP exam. It's most likely gonna be in the multiple choice, and like they're definitely gonna be in the free response question. So you really need to know like how, like, it's basically about labs. Like, how can you use different lab equipments to separate solutions and all that. So we're gonna go over that. We're also gonna go over the percent impurity equation. Here, I'm going to get a pointer, so this is hopefully helpful. Yeah, so we're going to go over the percent impurity equation. This is also pretty important. This was in the FRQ like 2 years ago, but this concept does pop up like very often. And also in your homework throughout the school year, this is going to come up. And we're going to go over a practice problem, and then we're going to do open Q&A, so whatever questions you guys have. And this is a little like thing to start the conversation, but if you guys ever have any questions on like AP Chem, or even like the format of the exam, or like any kind of like little like how to manage your time in AP Chem, like what are the most important concepts or topics to know, feel free to like ask it in the chat box. And I believe there's also like a special question box on this page. So yeah, so like use that, and I will get to the questions. So we're going to start off with the definitions. So mixtures and compounds. So like basically when we talk about mixtures, the opposite of mixtures is kind of like a compound. So mixtures are basically these like they're basically like this thing that has components. So a sand is like, so sand would be mixtures. You know, there's like different types of rocks, and the difference between mixtures and compounds, like they're both they're both combinations of two different types of like elements, or compounds. But like, they're both combinations of two different types of like substances. But the difference between mixture and compounds is mixtures, they are combined. They're not chemically combined. So they were not combined through a chemical reaction. They're kind of just like mixed together, you know? So like, let's say we have like a pile of stones, and then we have some like iron filings, and we mix them together. They're not like chemically bonded. They're just like mixed together. But like compounds, on their hand, they are chemically bonded. So for example, if we were to take the water molecule, which is H2O, right? So the water molecule is made up of two different types of atoms, the hydrogen atom and also the oxygen atom. So they're different, right? But they when they're chemically bonded, it functions as one. So the water molecule it functions as one. So it will chemically react as this like its own entity, you know. Whereas for the mixtures, if we have like hydrogen, oxygen in like a container, if we have it in like a mixture like stage, then they will be like two different types of compounds, and they're like two different types of entities. So like if you were to react something with like a mixture, the two different components of a mixture will have its separate reaction. So it will kind of like react separately. And this will be very important as we get on to like how we separate mixtures, because they're not chemically bonded, they don't react as like a whole, a complete whole. So do you guys have any questions so far? I know that might be a bit confusing. I know I was like really confused when I learned when I was like reading this in a textbook. Do you guys have any questions at all? Feel free to write it up in the chat. Yeah, so like I also one other thing, so in the textbook, I know a lot of times they talk about things like one type of atom or like one type of element. They're both terms that are used interchangeably. So like one type of element is equal to one type of atom. It's just something that they use. So you want to kind of like know that. Yeah, because I remember I still had a bit of like problem with this term, like the interchangeability of like element and atom, like even like halfway through the school year. So just to clear that out. Do you guys have any questions? Okay, so we're going to move on. All right, so now we're going to talk about pure substances versus mixtures. So pure substances, they're either like an element or they're a compound. So compound, like I said, it's like they're chemically reacted, they're chemically bonded, so they kind of act like a whole. And mixtures, on their hand, they're kind of, you see how they're kind of separate? They're not bonded anyway. Over here, you can see like some of them are bonded, but they're not like bonded with different types of, so like you can see the purple dots aren't bonded with the green dots. I think it's kind of hard to see here. But anyways, over here you can see that like the purple and the green, they're chemically bonded. But over here, there's still space in between those different, the different colored elements. So can you guys list any pure substances for me, like top of your mind, top of your head? Do you guys have any like idea what a pure substance would be? Like just any example? And copper. Yeah, so basically anything on the periodic table, they're all like pure substances. And all right, and I'm going to give one example here. I'm going to give the example of water. So when we're doing like lab experiments, oftentimes they'll ask us to use distilled water. Do you guys know why we use distilled water instead of just like old tap water, you know, or just like water out of your water bottle? Like, why do we use distilled water? So, yeah, it has things with other minerals. So like tap water, it's a mixture, right? Like, or it could, I mean, it could also be a compound if there are other things. Can compounds be a pure substance? Yes, compounds can be a pure substance. In fact, compounds are pure substances because compounds are basically things that already have like chemical bonds, so they kind of act as one. So like here, let me see if I can do like a physical representation of this. So let's say like I have two hands, right? One is hydrogen, let's give an example, and the other is oxygen. So when we're doing a mix, if let's say I were to make a mixture out of these two, right? I would like, so like they would be like this, right? They're floating around, but they're not acting as one, like it's like one entity. It's they're all separate, you know. They're all, so like if you were to add in water, or if you were to add in something else like highly reactant, you know, these two different elements, they're going to react differently. So like oxygen is going to react with water differently, and then hydrogen is going to react with water differently. So they're both going to act, they're going to react separately. But if we have it as a compound, so as a compound, that means that both these different elements are chemically reacted. So they're one, right? So they're floating as like one thing. So like towards the end of AP Chemistry, you're going to learn about polar stuff. So you're going to learn that even compounds, they have like different sides to them. You know, they have like the polar sides, but they still react as one though. So you're not going to, so like if you add in water, it's not like this part is going to go run away, you know, unless like the polar charges are so polar. But basically, you know, water is gonna, we're not gonna call water like separate. We're not gonna call water oxygen atoms and hydrogen atoms. You know, we're gonna call it as water. Are diatomic atoms elements or compounds? Good question. That they are elements. Okay. I guess you could, yeah, compounds are only made per, I'm gonna go on to the other screen. So compounds are combinations of two or more types of elements. So they have to be two different types of elements to be a compound. I hope that answers your question. And what characteristics would you need to determine if a compound is a pure substance, if it's not immediately obvious? That is a very good question. So so this is kind of not an existential question, but it's kind of something that like I really struggled with, and something that people can't, it's very arbitrary and it's very relative. So like with compounds, have you guys heard of like ionic bonds, and like ionic versus covalent bonds? Yes. Okay. So so here's a tough question for you guys. I think you guys are ready for this. So what's the difference between ionic and a covalent bond? Ionic transfers electron. Ionic has both anions, cations. right? So like if you look at the periodic, yeah, covalents share electrons. Yeah, so like if you look at the periodic table, like the official definition is if like I don't have a periodic table with me. Wow, I'm like I need to have this next time. But like so you know like the I guess you call the atoms on the opposite ends of the periodic table, they are kind of like the most different from each other, right? They have like so like I mean I guess like they have like very different electronegativity. This is a term that I don't know if you guys like are very familiar with yet, but we're gonna cover it more. But like technically if you so like ionic compounds usually are from like the opposite ends of the spectrum, right? They're so like the bond is like so strong. Whereas the covalent is like they're kind of the same. They're kind of like twins, right? Metals and nonmetals. So like covalent bonds, they're between two different atoms that are kind of the same. So they're kind of like siblings. They're just sharing stuff. Whereas ionic is like a parent and like a kid. You know, the parent has more control over what the kid does. It's not like you're sharing stuff. It's more like the parent is, or not the parent, but like the more electronegative atom is going to take more electrons. So it's going to be stronger. Like they have a stronger hand. They have a stronger attractive force. So so like there's a point where like let's say if you were to take a atom from somewhere around the middle of the periodic table, and you were to take another atom that's also like somewhere on the far end of the periodic table, then like is it ionic or is it covalent? You know, there's that middle ground that's like really unclear. And this is something that like in the end we don't really talk that much about ionic bonds. Hold on, sorry, I just like zoomed out on my screen. So like in the end we do still talk about ionic bonds, right? We still talk about like things that are on the opposite spectrum of the periodic table, but like there is that middle ground that's not very well defined, and like we just call it molecules in the end. We just call it compounds. We just call it things that have chemically reacted. But why can't ionic bonds contain bonds between two nonmetals? Yeah, exactly. It's because the two nonmetals, they have similar electric negativity. In case okay, so hydrogen is a very special case. Hydrogen is kind of like it has only one electron, right? So it's kind of like this thing that's like floating around, seeing if anything else wants its extra electron. So like if you guys know about like the complete, I think it's called like what's it called? So like the complete orbital, I believe. So like you need like 8 electrons for a complete orbital or 2 for helium. Hydrogen is like it's okay with this 1 electron. It's like it's okay by itself, but there are a lot of other like I guess like other elements that have like 7 electrons. So therefore they're gonna really want the 1 from hydrogen. I hope that makes sense. Yeah, why can't okay, I hope that answered your question. If it didn't answer your question, can you please put it in the answer box, and I will get to that later on during the Q&A. Okay, so I'm going to move on now. All right, I think I didn't answer the question by Mahfouz. Mahfouz, I'm sorry if I just pronounced your name wrong. I'm really bad with pronouncing names. Okay, so what characteristics would you need to determine if a compound is a pure substance if it's not immediately obvious? So, okay, so did I answer your question? I don't remember if I answered your question. If a compound is a pure substance. So basically pure substances just mean like if you like this molecule or this like compound, this chemically reacted thing is gonna react to different stuff like as one. So it's kind of like we're all in this together, you know, it's like we're already chemically reacted. Whereas mixtures, they're like separate, so they're going to react separately. I hope that makes sense. By the way, both of these are all mixtures. So mixtures, there are 2 types of mixtures. There's the homogeneous mixture and there's the heterogeneous mixture. The homogeneous mixture means that like so let's say milk, right? I think milk I believe milk is a mixture. I'm not exactly sure. I need to do more research on this. But like milk is a mixture. So like so like you won't see like little bits of like white specks in milk. You know, I mean, I guess it'll happen if it curdles, but like it's like the same throughout, even though they're not chemically reacted. Even so, you can see although these like different colored dots aren't chemically reacted, they're like evenly distributed throughout. And in heterogeneous mixtures, you can see there's like clumps of different elements, so they're not evenly distributed. It's kind of like, let's say if you have this like things of different density, you can see that like they're separate. Okay, so yeah, so we were talking about water. So distilled water is a pure substance, right? It's purely H2O. There's no like added stuff to it. There's no like sand or like minerals, as I think Natalie said. So like if you add contaminants to the pure water, then it would be considered a mixture, right? If it didn't like chemically react with the H2O, which I mean, if it's water, it's still H2O. It's not like chemically reacted. It's not like H3O or something. So yeah, so that's why we use distilled water in like our lab experiments, because we want like pure water. We don't want something else with like a extra like mixture or extra copper in it or something. All right. So here's like a fun activity. So mixtures, homogeneous or heterogeneous. So like we're gonna start with this picture over here. Is coffee homogeneous or heterogeneous? So I think the one on the far end, I would consider it a homogeneous mixture. Right, the far end, I believe it's homogeneous. But like these are these lattes? I believe they're lattes. I don't drink coffee, so I drink tea though. I know tea is like kind of heterogeneous. There's like these bits on the bottom if you let it settle for a while, but mostly homogeneous. Right, so for lattes, I believe they're kind of heterogeneous because you add in the cream, and the cream, like if you don't mix it thoroughly, they're separate, as you can see. Like that's how you make latte art. And here in smoothies, the same thing, right? You know, like this layer may be homogeneous, and this layer may be homogeneous. But if you were to look at this like thing as a whole, it would be heterogeneous because they're not like the light pink stuff is not evenly mixed with the darker pink smoothie. So anyways, that was just a little tidbit. All right, so now we're going to go into separating mixtures. So like I said, this is a huge topic on AP Chem, and I think that it's going to be really helpful if you guys like really understand this before like you dive into the lab stuff. Wait, have you guys started labs yet? I'm curious. Yep, you have. So what kind of labs have you guys been doing? Have you like separated mixtures? Okay, not me. Yeah, so like fun fact about me, I'm homeschooled, so I took AP Chemistry online, and I have this like lab kit. It's actually in my basement right now over here. But yeah, I had a lab kit, and I have like all these little assortment. Like I have this whole assortment of little like squeeze bottles full of different acids and chemicals, and I would like combine them and stuff. So like with labs, I actually like would do a bunch of labs like in one. So like I would just do, anyways, that's I'm going off topic. Anyways, we're gonna go into separating mixtures. So mixtures are made of different components that have different properties, right? So they're different. They're not chemically bonded, right? So therefore we can have different separation methods. So we have distillation, which is mostly used for liquid mixtures. We have filtration, which is for mixtures that have both solids and liquids, because filtration is kind of like you're literally using like a sifter to sift through to kind of separate the solids from the liquids. That's filtration. And chromatography, it compares liquid mixtures. So we're going to go into that. All right, so distillation. So for distillation, you separate components in liquid mixtures. So let's say we have like a liquid mixture, and this blue squiggly line represents the liquid. All right, so what happens is we heat this substance in this glass this glassware. So we heat it, and then the component that is going to evaporate the fastest, so the component that's most easily evaporated will evaporate first. So therefore, let's say we have water and salt, right? So salt doesn't evaporate that easily. Salt, like you have, I think like the boiling point of salt, it's very, very high. Like, so water is going to evaporate first. So therefore pure water is going to go up the tunnel. And so yeah, so which component of mixture is going to evaporate the easiest? So that is literally what distillation is all about. It's literally trying to find out which part of this mixture is going to evaporate first. And usually, by the way, when we start with like these labs, we know what is in a mixture. So we're not gonna just be like, oh, I have no idea what's in this solution. You know, usually you know like what's in the solution. So like usually with distillation, for example, usually you're trying to compare two different components that's in the mixture. So you're trying to see, oh, like which one of these two is gonna evaporate first. So you're not like, so it's not like you have like 10 different components in this mixture, because that would be kind of messy. You know, what if two different components have like the same or have similar evaporation like temperatures? So yeah, so we're basically looking at which component of the mixture evaporates at the lowest temperature. Does that make sense to you guys? So like the lowest the part of the mixture that has like the, I guess they're called the most volatile. So it means they are more like excited to evaporate. Do you guys have any questions so far? We can move on to the next slide. This is just a distillation. All right, so this is still distillation. It's kind of like a big picture thing. So basically over here, there's a heater, right? And the solution's in this glass tunnel. And we also have a thermometer usually just to make sure that we're not like overheat, like we're just, you know, we're heating the solution too fast. We're trying to keep it at a consistent temperature usually. But yeah, so like the solution will be heated and it will go up this glass tunnel. It's going to go through this thing called a cooling tube. So the cooling tube is where like it's going to condense and then it's going to drip down into this other test tube, or sometimes we have like, yeah, so that we can like measure how much of this mixture is in the solution. So usually we'll like wait until basically all of the one component that we're trying to find or trying to get out is all evaporates, and then we can like measure how much of this component was in the original solution. So does that make sense to you guys? If you have any questions, drop them down in the chat box. All right. So I'm going to move on to the next type of separation, mixture separation. So filtration. This is the easiest one to get. I have another picture of coffee here because aesthetics, right? Like it looks pretty. Yeah, so basically you put a mixture on a mesh. So like here, like a coffee filter, right? To separate the solids from the liquid. So it kind of just filters the mixture. This is like something that's very easy to get. I think, have you guys ever visited a dinosaur museum? I know like I used to visit dinosaur museums and I had this like little sifter and I would sift through the rocks and like, you know, get out like I think they have this like you're pretending that you're sifting for gold, you know, so like the gold nuggets, I think, or you're trying to sift out the sand or something. I don't know. But yeah, it's literally just separating the solids from the liquid, usually here. All right, so this one is called chromatography. This was on the FRQ, I believe, this year. Yeah, I was going to say last year, but it was in the exam this year. This is comparing liquids. I actually have chromatography papers right here with me. I was setting up for a lab. So basically, I'm going to explain it first. So basically, we have the samples of different mixtures that we want to compare here at the start line. Right, so this white thing right here, it's like slightly gray. This is a piece of paper. So I have a piece of paper right here. I hope you guys can see this. It's a piece of paper. So you basically put it in a solvent. right? And what's going to happen is the solvent is going to travel up the paper. And as it travels up the paper, it's going to carry all these different samples of mixtures up with it. So like if you guys have ever like written on a piece of paper like with pen or something, and then like if you run it down with water, you can see like how the pen, like how the ink runs with the paper, or I guess it kind of runs with the water, right? But like it kind of forms a streak across the paper. So this is kind of what's happening. So the solvent, so like the solvent is going to travel up, it's going to carry the mixture with it. So what's going to happen is, so the solvents, they're all going to travel upwards, but they're all going to travel up at different speeds because they are different mixtures. So this is how we're going to be comparing the different mixtures. We're going to see how fast they travel in relative to each other. So chromatography, it compares mixtures based on their attraction to solids and liquids. So the paper here is the solid in the scenario, and the solvent is the liquid. So basically the liquid is going to go up this piece of paper, and it's kind of like a battle. It's kind of like, okay, so this mixture, is it going to like the solvent, the liquid more, or is it going to like the paper more? If it's going to be more attracted if it's more attracted to the paper, that means that it's more attracted to the solid. So if it's more attracted to the paper, then it's going to move up slower, because the water's going to, or I mean, not the water, sorry, the liquid's going to go up at like the fastest pace, right? So we're kind of seeing like which mixture is going to, if the mixture is traveling at the same speed as the solvent, as the liquid, then that means that they like the liquid a lot more than paper. So they're going to cling on to the liquid like more than they cling on to the paper here. So this is what's going to happen. So it's going to like travel up. This is kind of a bad picture, honestly. Like there's usually a streak that goes on with this. So like for each mixture, there's going to be a streak. But let's say like after 10 seconds, or usually it's like after like 5 minutes or something, you will see something like this, right? So you'll see like, okay, so mixture X is traveled this far, mixture A traveled this far. So you can see over here, the ones that travel slower, they cling on to the paper more, so they're more like reluctant to go with the liquid, right? So so like they all start with at the same starting line, and they go up. So mixtures with stronger attractions to the paper cling onto the paper, so they travel slower. And those with weaker attractions to the paper, they travel faster because they go with the liquid. All right, so does that make sense? Is everybody getting it? Does anybody have any questions so far? Yeah, if you guys have any questions, like anytime, just drop them in the chat box. I'd be happy to answer them. So yeah, so basically I have, I think I was going to compare two different sets of mixtures. Oh, wait, never mind. I have like, okay, so you can see all these different dots. Let me see if I can show you guys the camera. Okay, I do not know how to stop my screen sharing. Hold on. Okay, stop screen share. All right, so here you can see this piece of paper. I don't know if it's gonna focus. Anyways, there are these different dots on here. All right. And what I was going to do, so I have these two different papers. So what I was going to do is I was going to put them to do two different solvents and see which solvent is going to carry them up faster. That was something else that I did in Chem Lab. Okay. Hold on, I'm going to pull up my screen again. All right. So can you guys see my screen? All right, I think you guys can. Okay, so we're going to move on. All right, so now we're going to talk about the percent purity equation. So to calculate the percent purity equation, percent purity of a solution, we have to first have the mass of the pure substance, and then we're going to divide it by the mass of the total impure substance, and we're going to time it, multiply it by 100%. So that means, like, let's say we have a solution of something, and then let's say we want to measure, we want to know how much of this so let's say we have like a solution that contains sugar and water. So we want to know how much sugar, so like what percentage of pure sugar is in this solution. So this is kind of like the purity. So we could say like 60%. So like, but this solution of sugar is 60% pure. So that means like 60% of the mass is sugar, is pure sugar. All right, so we're gonna move on. All right, so I have a practice problem right here. This is something that comes up on the AP exam a lot. So this is like a very simple problem. The mixture from an experiment contains salt and water. So the mixture in the flask contains, it weighs 150.0 grams. So what is the percent purity of the water? So what percentage of the solution is pure water? So here we're trying to calculate the purity of the water. So what is the first step? What is the first step? Do you guys know? Drop your ideas down below. It's okay, like if you're wrong. We all learn from our mistakes. I learn from my mistakes a lot. So yeah, so basically what we're going to do is we're going to use one of the techniques of separating mixtures that we just learned and apply it to this problem. So we know that we have to have the mass of the pure substance, and we also have to have the mass of the total impure substance. And we know that like the solution, which is impure because it contains two different types of it has two different components that are not chemically bonded. So salt and water, they don't chemically bond. So we know that 150.0 grams is the total mass of the impure substance. So how are we going to get the mass of the pure substance, which in this case is pure water? So do you guys know how we're going to get the mass? So like what kind of techniques we could use? So as a quick review, we have three different types of ways to separate mixtures as of now, right? That we've learned so far. These are the three like most common ones that like we use in chemistry. So we have filtration, we have distillation, and we have chromatography. So which one do you guys think is gonna help us in this problem? You guys have any idea? So this was actually something that was asked this year on the AP Chemistry exam. They actually asked us like what type, how are you gonna find like this part of the solution? It's pretty important. So do you guys have any idea? I'm gonna give you guys the answer. So for salt and water, it's basically like solids and water, right? Although like salt, honestly, wait, never mind. They're not solids. It's like, so the salt has already dissolved. It's not like a piece of rocks in water. So it's not like you can filter it out. So filtration is not an option for this. What about chromatography? Do you guys think chromatography will work for this? So like putting it all on a piece of paper. Do you think that's going to help? So remember, like with chromatography, we're trying to compare different mixtures. We're putting different dots. We're putting the dots on the piece of paper, right? We're the different mixtures. So here we only have one mixture, so we can't really compare anything here, right? We don't have like a separate like salt mixture and a separate salt solution, pure salt solution, and a separate pure water solution that we want to compare. They're not mixtures actually. But like, so yeah, chromatography is kind of comparing mixtures. So here we're not really comparing mixtures. We're just trying to test one mixture. So therefore, we're going to use distillation. In distillation, so yeah, so we're going to try to separate the salt from the water. So what we're going to do first is we're going to heat the solution until all the water evaporates. So we know that water evaporates at a lower temperature compared to the salt. So water is going to evaporate first. And then we're going to collect the water in another clean flask. Okay, so this is something that we need to know. So we need to know the mass of the flask, so that we, like, when we weigh the flask that contains the pure water, we don't like we don't suddenly realize like, oh wait, I don't know like what the mass of this flask is, of the container is. And then second, we're going to weigh the water. So we're going to get the mass of the pure water and then subtract the mass from the flask, like subtract the mass of the flask from the value. So let's say that the mass of the pure water is 50.0 grams. So next we're going to plug it into this equation. So remember we have 150.0 grams of total impure substance, and we calculated that we'll just say that the mass of the pure water is 50.0 grams. So plug it all in there. So this is behind the solution. So percent purity would equal to the mass of the water divided by the mass of the water in salt solution, which is like the impure mixture, right? And then we will multiply that by 100%. So the total percentage of purity would be 30.0% with respect to pure water. All right, so if we were to flip this on its own head, if we were going to say, oh, I want to see what percentage of this total impure substance is made up of pure salt, not pure water, but pure salt, then it would be 66.6% with respect to pure salt. Does that make sense to you guys? Give me a thumbs up if it all makes sense, and I will move on. I think we're going to cover one last topic for today. Do you guys have any questions so far? Okay, so I'm going to move on, and we're going to talk about alloys. This is something that's going to be pretty important. Do you guys know what alloys are? If you know, could you like put it down in the chat box? So like if you guys have an example of an alloy, feel free to put that down as well. So yeah, two metals, right? It's kind of like a metal mixture, right? It's not that they're chemically reacted. So yeah, so metallic, solid. So most of the time, like let's say copper metal, right? Solid copper, it is a metal. If we have pure copper, it's pure copper. But sometimes we add alloys. We add, don't add alloys. We add different like other things. Sometimes it's hydrogen, I believe. Sometimes it's carbon. Those are some of the common things that we add in. So so here we have a pure metal. You can see all it's all red dots. They're all the same element. And now we have this substitutional alloy. And this is when we kind of like take some of the red dots out, right? We take some of the red dots out and we replace it with another type. It could be a metal. It could be, it could be copper, I think, or no, not copper. It could be carbon. Carbon is something that we use quite a bit, I think, in alloys. And we put in, and they're of similar radii size, right? So it's not like we take a teeny tiny bit, a teeny tiny circle or a teeny tiny element that's like disproportionate to like the red dots, right? We put it in here. No, like you can see the blue and the red, their size is fairly similar. If you look at the green dots over here, their size is nothing. It's like the size difference is much greater than the blue versus the red. So so over here in substitutional alloy, we substitute atoms in the lattice with similarly sized radii. So the result of this would be a change in hardness. So this alloy will have a different hardness than this pure metal, right? And here, this is another type of alloy, the interstitial alloy. This is when we take this pure metal and we add in these like little other types of like these little other foreign, you could say like element or metal, and we put it in between their lattices. So we don't substitute it. So over here you see in the substitutional, we take like the red ones out and we replace it with like, with another compound or another element. But over here we put it in between, and this makes it more rigid so that it's like harder to bend. It's less malleable. So like in metal, like gold, right? like pure gold, we could, if we were to like hit it with a hammer, it would be malleable. But over here, if you wanted to make it less malleable, we'll add in these like these different elements that have different radii sizes that kind of makes it more stiff and less malleable. Okay, so that is it for the stream. So do you guys have any questions so far? Or, I mean, this is it for the stream. So feel free, like, definitely follow us on our social media because we have a lot more streams coming up for AP Chem. I know this is like it's the first week of school for you guys. Like, my school started 2 weeks ago, which is kind of early. I know in some states, like, it's illegal to start school before Labor Day weekend. So, yeah, so, like, I know a lot of people, I have a lot of friends who started school, like, this Thursday. So, I know, like, we're still pretty early. Like, we're still in the very early stages of AP Chem. So, yeah, so we have a lot more streams planned up for you guys. Do you guys have any questions? Like, in regards to the exam or in regards to, like, the most efficient study method, or, like, what materials, or like, the topics that you guys are currently in? Or, like, questions about the FRQ part of the exam? I know that was something that I was, like, a little bit confused on. Okay, I think, let's see. So you guys, you don't have any questions? How are you guys feeling about AP Chem? Could you list some example of Chem FRQs? Yes, so in my next stream, I will be sure to do that. So, like, for this stream, there wasn't, like, anything that was super specific. Like, so, like, the thing with FRQs is they mix different topics together. So, like, they might take something from, like, chapter 15 and then mix it with something with, like, from chapter 2 or from chapter 3, you know? So it's, like, it's a mix. So, like, it's really hard for me to just, like, take one FRQ and be able to say, okay, so, like, today we learned all the topics on this FRQ and we can, like, fully, like, answer this whole question. So it's kind of hard. Really, like, it's at the end of the school year that you kind of take all of this knowledge together and you can answer some FRQs. But actually, so the practice question that I just used here, this was I think this was one subsection of an FRQ, I believe, from like 2 years ago. And I remember this year they also used something related to this. So this equation, it's very useful, and this, like, method that we use, like distillation, it's all gonna be on AP Chem exam. Like, you're gonna have to devise your own experiment, I believe, in one of the FRQs. So this is all related, but, like, I'm trying to, like, find something that is, like, covers purely what we just talked over today. So do you guys have any more questions? How are you guys feeling about AP Chem? I think I asked this at the beginning, but are you feeling overwhelmed, or are you just super excited for the school year? Have you guys taken Chem before, like honors Chem or regular Chem? I took regular Chem before AP Chem. A bit overwhelmed at the beginning, but I'll manage. Yeah, I think, honestly, you just pick up study skills as you go, because for chemistry, it's super conceptual. Like, it's not so much like math. You know, for math, like, you have to keep, like, practicing different problems until you, like, you can get it. I mean, chem is kind of the same. You do problems, but there's not as much busy work. It's more about understanding the concept and being able to, you know, use that to apply to different problems. But it's not like you have to do 100 problems to be good with the concept, you know. So, like, I would recommend just knowing, like, just really understanding the concept. So if you wait, oh my goodness, I'm so sorry. So were you guys looking at my presenter view the whole time, like this timer thing, like towards the end? I just realized that. I'm so sorry about that. Okay, here, I'm gonna change the screen sharing. I realized you guys were looking at my timer, like my speaker notes thing, instead of my slides. I'm so sorry about that. Wow, I did not look at this. Okay. Okay, that's why you couldn't like read the question. I'm so sorry. Hold on. I have no idea how to change this. Okay, so what kind of like study methods are you guys currently using? Like, how are you studying chemistry right now? I can give some tips if you guys want some. I know everybody learns differently, but I know like for me, like I try different methods, and in the end I realized like just like having condensed notes or like my teacher gave us really condensed outlines, kind of like this, you know. So he like he didn't really like want us to read like the entire textbook. Okay, so I might try Cornell notes at one point. Yeah, that's a good idea. So I think like just having like general concepts in your head. So whenever something's really confusing, right, you want to take the time to work it through. And once you get it, kind of like try to come up with a way to explain it to someone else, and then write it down in your notebook so that whenever you're reviewing that topic, you can go back and see, oh, okay, so that's how this works. Because a lot of time, because by the end of the school year, you're gonna realize like you don't have time to read the whole textbook all over again. You don't have time to read over all your notes. You want to have some things that kind of like help you trigger the memory back and help you like remember like, oh, this is how it works. And I will have a lot of these like little like, I guess these like ways, like little tricks to learn different chemistry things. So like there's this one called like follow the alligator, where like there's it's called the equilibrium alligator. I don't know if you guys have heard of it, but it's basically so with equilibrium, if there's equilibrium, if you add more substance to this one side, it's gonna make the reaction faster on this side, and it's gonna go on to the other side. So that's like equilibrium. So basically there's like this whole like alligator little animation that I can show you guys, and it really helps like remembering that, like especially on AP Chem exam, because like you can't just sit there and think it through like all the whole time. It honestly is like kind of instant recall and being able to apply like your knowledge to things immediately. Okay. Are you guys taking have any of you guys taken bio before? So like I think bio and different. Like I remember biology, there's like a ton of memorization. And for chemistry, it's like super conceptual. So I really like chemistry. And I'm currently taking physics. And it's also super conceptual. So yeah. So do you guys have any more questions for today? If not, I hope to see you guys again next time. I will try to put more FRQs into my questions or into my slides. And feel free to come to us with like any questions. We're gonna have Q&A at like I believe almost every live stream that we have, unless we run out of time. But yeah, like feel free to come to us with questions. We would love to share our study strategies with you guys. So any more questions? No more questions? Okay. Well, guys, thank you guys for joining. I hope to see you guys again soon. Good luck with the AP Chemistry. If you have any questions, like just present them or take them to the next live stream, and we'll be happy to answer them. So yeah, good luck with AP Chem. And have a great rest of your week. I mean, today's like last day of the week, but have a great Saturday night. Bye guys, see you guys in the next stream.